All right, guys. Sorry, it took some time to set up stuffs, but now I think we're ready. So today we'll try to look into um, the concept of energy gap or band gap in a crystal. Have you heard about this term band gap previously? Right? Do you know that semiconductor material has some band gap? Is it new to you, or you knew about it? Okay. All right. So today we'll try to see that where does this band gap come from? Okay. Um, because of the band gap, we have some strange behaviors of semiconductor. For instance, you know that if you try to uh, uh, push current through a diode, you have to apply some certain bias, right? Before you apply a threshold voltage, the diode won't conduct any current, right? And these property arises from the band gap behavior. Okay, it's also the same stuff, the band gap stuff, which makes MOSFET work beyond a certain threshold voltage. So after you apply some certain threshold voltage, MOSFET switch on. So we will want to see that where does this band gap come from? In fact, this is something that only quantum mechanics can tell you. No classical behavior can be used to explain this stuff. So let us see. We knew that if you have a single isolated atom, then the Kronig-Penny, then this atom is supposed to have some particular energy gaps, right? So I'll try to draw here. Okay. So we knew it that if I have some potential well, quantum well, then electron can only exist in some few possible energy states. Okay. So this is the first energy states, and this is the second energy state, so on and so forth. Okay. We also knew that if the potential well is infinite, then all these wave functions would be completely inside the quantum well. But if the potential well is finite, let's say at the very bottom, potential is 0, and outside of the potential well, it has some finite value, then the energy and the wave function is going to spill a little bit beyond your potential well. Okay. We also knew that the amount of spilling of this wave function, it depends on, it's actually described by a factor alpha, and alpha depends on the difference between the potential and the energy. Okay. So if the value of V naught minus E, if the value of V naught minus E is very high, then alpha is also going to be very high. Okay. And if alpha is very high, then how does it impact the spilling behavior? Outside the potential well, the wave function is described as phi equal to C e to the power minus alpha x. So if alpha is very high, very large, then phi is going to decrease very rapidly outside the potential well. Okay. On the other hand, if alpha is low, then phi is going to decrease very gently. So this is why the first energy, the ground state energy, will have very small tail outside the potential well. Whereas the second quantum state, they will have a slightly larger tail outside the well. And you can guess that the third quantum state, which will have an even higher tail, right? And the third state will probably look like the following. Okay, so the higher you go, the higher energy you have, the longer tail do you have. Okay, so if I bring two wells, quantum wells, close to each other, which energy state is going to be impacted most because of bringing two different guy at close neighborhood? Is it the first quantum state, or second quantum state, or the third quantum state? Which one have the third one, right? So the higher that you go, the more the impact, okay, because it has the longer tail, right? All right. So this is what we discussed in the previous class. It's just a reminder to you. And we also discussed the following, that if you have two quantum wells, then the energy states is going to be splitted into two different values, okay? We gave an example with two mechanical oscillator. We said that if I have a spring mass system, then the spring mass system have some particular frequencies, right? And that particular resonant frequency depends on the mass and the spring constant. If I bring two different spring mass and couple them together, then instead of having a single resonant frequency, they will have two resonant frequency, okay? And interestingly, if you just bring more and more uh, spring mass system, couple them, all of them together, they will have more and more energy splitting. The number of energy splitting is just dependent on um, how many spring mass you are actually coupling, okay? So if there are n number of spring mass system all coupled to each other, you will have n number of resonant frequencies, okay? In a similar way, if you bring two quantum wells close to each other and let those wave functions interact with them, then you will see electrons energy is also going to be split into two different values, okay? So let's say before you bring those quantum wells, maybe you had an energy here, you also had an energy here, but after you bring those two quantum wells close to each other, now instead of having energies at this value, you will have a new energy level, which I should write with a different color. So now let me try this. I will have a new energy which will be slightly above and slightly below. Okay, same stuff here. Okay, slightly above and slightly below. If I bring three quantum wells, then the energy would be split into three different values. Okay, so instead of having this guy, maybe I will rewrite it like the following. If I bring three wells, I would have three different values. Okay, and same stuff here. Okay, so if I bring n number of atoms, then there will be n number of energies. They're all splitted and they're very close to each other. Okay, so question to you guys. We knew that previously, before you bring many quantum wells, there were maybe one or two eigenstates, eigenenergies. So one was very close to the bottom of the potential well, and one was above the potential well, right? So these second energy state, they are also going to be splitted, okay, into the same number of values. So if you bring three quantum wells, you will have three different energy levels at each of the states. Okay, the more number you bring, the more splitting will occur. All right. So if I bring infinite number of quantum wells close to each other, these energies would have a value of infinity, right? So this means that you won't be able to identify any discreteness of energies between these values. So they will be so close to each other that you can just imagine that these are just continuous energy states. Okay, these are just continuous energy states. If I bring infinite number of quantum wells close to each other. Okay. So did you notice that when I drew this graph, I said that energy is going to be infinite, but I intentionally left a gap open here, right? I intentionally left a gap open here. I did not fill this up, right? And it was intentional, and it is actually correct that if you try to bring more and more quantum wells, you will see that no matter how many quantum wells you bring, there will always be some certain gaps between those energies. Okay? You will never be able to fill this up. And today we will try to see that why, no matter how hard you try, no matter how many quantum wells you bring, you will never be able to fill this gap. There is some certain values of energies which are always forbidden. You cannot have energies at this level. Okay, so we'll try to see that why we have an energy gap. So let's see that how people actually modeled it. So Kronig and Penny, these two scientists, they first proposed a model to explain the behavior of energy gaps in a crystal. How they did it? They did the following thing. So they started with a single atom. They know that a single atom have many different energy states, right? So a single atom have many different energy state, E1, E2, E3, 4. If you bring multiple atoms close to each other, then the potential well would become finite. Okay, look at the single atom case. The potential well is actually infinite as you go away from the nucleus. Okay, it just keeps increasing. But if you bring multiple atoms close to each other, then the potential well would take a U shape. Okay, because every time you take an electron out of an atom and go close to another atom, the potential well starts to drop. Okay, so this is the reason of the U shape. Now, Kronig and Penny did the following. They knew that analyzing these U-shaped potential well is very difficult. So they approximated this entire function by a much simpler profile, which looks like this. So I'll show it here. So instead of this U shape, they created the square shape. Okay, and the reason is that if you make this square instead of this U shape, the corresponding solutions becomes much more simpler. Okay, so with that simple approximations, they came with a formula that relates the energy and the wave vector k of a electron. Okay, so what is the energy and the wave vector relation for an electron in a single quantum well? Let's see. So in a single quantum well, let's say infinite quantum well, I know that the energy states is related to h square k square divided by twice m. If you forget that, where does this come from? I wrote it in previous class, so check your class notes. But here is a quick reminder that energy is related to momentum square divided by twice m. Okay. If you still do not remember it, this is the relation that you must remember from your high school, E equal to half mv square, right? So from there, I just changed it. I wrote it mv square, that is the momentum, divided by twice m. So in quantum mechanics, we know that this momentum mv is related to h divided by lambda. In other words, it has the following relation, hk. Okay. So this is where I got this relation between energy and the momentum. Okay. So in classical mechanics, if I ask you to draw the relation between momentum, mv, and energy, how it would look like? You know this relation, right? E is equal to half mv square, right? That means mv square divided by twice m. So if I draw energy versus mv in classical mechanics, how this shape would look like? Is it a straight, would be a straight line? How it would look like? Parabola. It would just look like a parabola. So it would start at 0, right? And then it will go like a parabola. This is exactly the behavior of an electron. The only difference is that instead of writing mv, we write k. Okay, k is the wave vector. Remember that mv is related to h by lambda, or we can also write it h cut k. Okay, so this is how k and mv are related. So in case of electron, we also have the same behavior, E equal to k. E equal to, E is proportional to k square. All right. So Kronig-Penny, he showed that if you take many quantum wells, then instead of having this simple parabolic formula, you have a slightly different formula. And the formula is written like this. P sine alpha A plus cos alpha A is equal to cos Ka. It may sound that what I'm actually talking about, but I will explain it in a bit. Just hang on a second. So they gave this formula that if you have many quantum wells, if you have many atoms in a chain fashion, in a periodic chain fashion, then the energy and K would follow this following relation. Okay, here, let me break it down. That what is this P prime? P prime is actually M V naught PA by H cut square, and alpha is actually twice ME by H cut square. So the bottom one would actually tell you that what is this relation with the atomic structure. For instance, look at this value of P naught, P prime. It depends on M. M is the mass of electrons. P is the potential well. Okay, so how high the potential well is given by V naught. Okay, B and A, these are both actually space. So A actually determines that how wide the quantum wells are, and B determines that how far each of these quantum wells are from each other. Okay, so if you make these atoms very close to each other, the value of B will go down. Okay, On the other hand, if you make those quantum wells very narrow, then A will go down. And V naught, as I said, that V naught determines that how big, how high your potential well is. Let's come to alpha value. Alpha square is related to the mass and the energy of electron. Okay. And then you have the value of K. K is the wave vector. So we are not going to derive that how it came into being, because I think it should be related to the graduate class, like more higher level class. But for now, let us go with their prescriptions that it follows these relations. Now, using these relations, we want to see that why an energy gap could be appearing in a one-dimensional crystal. So how do I know that how to plot the energy and K from these equations? So in order to know that, we will use a particular program. Okay. Let's see. Give me 1 second, guys. Man. Oh, at last. All right, so let's get back. We said that we want to plot the relation between energy and K. So we know, to remind you one more time, that we know that in case of a single atom, E and K follows a very simple relation. It's parabolic. Okay. This K and this E. In case we want to know that what is the situation of E and K in case we have many quantum atoms all periodically arranged. So in order to find that out, we will plot this guy first. We will plot this left-hand side of this equation. So look at this. The left-hand side of this equation, it contains P prime, alpha, something. The right-hand side of this equation, it contains cos Ka, right? Now, we do not know what is the value of K yet. K is the wave vectors, I know. A is the value of lattice parameter, okay? How far apart each of these atoms are. Now, no matter what is the value of K and A, we know that cos Ka, it cannot have a value more than 1, right? it also cannot have a value less than 1, right? So if that is true, we must also recognize that no matter what, the right-hand side, the left-hand side of this equation also should have a value which is confined between -1 and +1, okay? It cannot have a value beyond +1 or less than -1. If so, look at that. The left-hand side of this equation, it is a function of energy, right? It's a function of alpha, and alpha is a function of energy. So if you plug in a value of energy in the left-hand side of this equation and see that the left-hand side becomes takes a value of greater than 1, we know that this energy is not going to be a solution of this equation. Okay, so this is what we will try to see through plotting in Mathematica. So what we're doing here is this. We took the left-hand side of this equation, P sine alpha A plus cos alpha A, and we try to vary the value of alpha A. Okay, remember that alpha is a function of energy. Okay, so when we change the value of alpha, we're actually changing the value of energies. So we will do the following. We will try to plot this function by continuously changing the value of energies. Okay, and we'll try to see whether the function remains in between +1 and -1. Okay, so here is the thing. Let's start with a value of p equal to 0.01. Very small value, okay? Remember that what is p? P is a function of m v naught ba, right? So if a small value of p naught actually means a small value of v naught, okay? So that means the potential wells, the periodic potential well that you see from the crystals, these values are very small, okay? These heights of these wells, this depth of the wells are actually very small. So that corresponds to a small value of p naught. So if p has a very small value, I'll try to see whether the right-hand side of the function remains in between negative and +1. So here you go. You see that the value of these right-hand side of this equation, it remains within +1 and -1, you see, which is shown by the green curve and the yellow curve. But if I make p bigger, remember that making p bigger actually means that you either increase the value of v naught or you either increase the value of b and a. V naught means how deep your quantum well is. So instead of having a shallow quantum well, if you have a deep quantum well, okay, a deep quantum well, then the value of p naught would increase. So if p naught has a high value, so instead of 0.01, let's say 10, okay, I make it increase by a factor of 1000. Now let us try to see whether this function remains in between -1 and +1. Okay, there you go. So these horizontal lines are showing the -1 and +1 value. Do you see that sometimes this function actually goes beyond +1 and sometimes it goes beyond -1, right? So whenever it goes beyond -1 or beyond +1, those energies cannot be a solution of this function, okay? Because we know, one more time, how do we know that this is not a solution of this function? Because we know that this function, this left-hand side, cannot have a value of more than 1 because the right-hand side is actually cosine value, okay? So whenever it goes beyond +1 or beyond -1, those are the energy states. Let me show you with the cursor. So this is the energy states. These are the energies which are forbidden, which are not allowed to be a solution of a quantum chain of quantum wells. Okay, same thing here. These energies are not allowed. Okay, only this energy is allowed. From this to that, these energies are allowed. Again, these energies are allowed, but not beyond these values. Okay, So this is how we know that if we bring multiple quantum wells arranged in a periodic fashions, you cannot have some particular energy values. Okay, these are actually the forbidden energy gaps, and this is where the energy gap or band gap arises. Okay, so in a periodic potential well, the bottom line is that in a periodic potential well, there are some certain forbidden energy gaps. Okay, I'll show you with one quick simulation here. So in case of a single quantum well, you know that the energies are discrete, right? So these are the different energy states for a single quantum well, right? For instance, this is the first energy states. This is the second energy states, third, fourth, fifth, sixth, so on and so forth. If I bring two quantum well, then I say that each of these energy is going to be splitted into two values, right? So if you had previously 6 energy states, now you'll have 12 energy states, okay? So let's see, what do I see for well pair? So if these wells are very separated from each other, then it has its own quantum energy states. But the moment I bring them close to each other, you'll notice that the energy states is going to be splitted. Okay. Do you see this? This energy split is energy is splitting into two values. So now let's go back to many quantum wells. So do you see this? In a many quantum wells, these energy states, they have been split into many, many values. You see this? There are many, many values. There are many, many values. And also interestingly, looks like that no matter how many energy states are there are always some gaps in between one bunch of energies and another bunch of energies. So although energy is splitting, but they're not splitting all over the space. They're actually bunching. Okay. So we can say that instead of one ground state, there is a bunch of ground state. Okay. And then there are, so this is the first bunch of ground states. Okay. And then you have some certain energy gaps. Nothing is in between them. Then you have second bunch of states. Then again, there is an energy gap, which is third bound states. Okay. If you reduce the number of wells, you can also see the impact. Let's say we start with a single quantum well. You have just 3 states. Okay. Make it 2. You know that if I make it 2, I should have 6 energy states, right? Let's see. Is it visible from here that it has 6 energy states? Do you see the white marks? So if I keep increasing the count of the wells, you will see that instead of one energy, now it has 3 different energies. So if I have many, many quantum wells, you'll have many, many energies. But regardless of how many energy states you are splitting, there will be always some certain energy gaps. Okay. Now correlate this thing with this function, where we say that at some point, there are some particular energies which will go beyond +1 and -1 values. So those energy are not allowed. So these corresponds to the gap in the energies. Okay, so here are those energies lying, which does not obey this plus and minus bound, and that's why these energy states are not a solution of this system. Okay, so I think we are pretty much up in time. Let us continue our discussion from the next class. Thank you, guys. We'll see you in Friday.